All right, well here, let's continue. Again, I'm going to do an example here that you may have seen in class or it may be new. Of course, if you've seen it before, you're welcome to skip it. All right, we had written down the formula for the potential of an extended charge object, written as a series of terms, okay? And then last time, we looked at the different terms in this series. So this sum is equal to the sum of the first term, where n equals 0, which is just 1 over 4 pi epsilon naught r times the integral of the charge density integrated over the volume. Okay? Of course, the integral of the charge density over the volume, that's just the total charge, right? In any event, this term is called the monopole term. The next term in the series looks like this. 1 over 4 pi epsilon naught r squared times the integral over volume of r prime times the charge density, okay, times cosine theta prime d tau. This term is called the dipole term, or the dipole potential. The next term, well, the series continues forever. Here, let's write down one more term. It's 1 over 4 pi epsilon naught r cubed. Note they drop, each successive term drops off faster and faster compared to the ones before. And then we have integral over the volume of r prime squared times the charge density times this term, the second Legendre polynomial, 1/2 3 times cosine squared theta prime minus 1 d tau. And this term is called the quadrupole potential. Well, the series continues, but we're not going to continue. We'll stop there. Okay? Very good. So the first thing we'll look at is a charged rod. So this is a segment of length L that carries a charge density lambda, all right? And what we'd like to do is to find the first two terms in the multipole expansion of the potential. So the monopole term and the dipole term, all right? So, well, this is easy to do. Just using the expressions we just wrote down. So the first term, what I'll call V monopole, this is just 1 over 4 pi epsilon naught r times the integral over the charge density of the charge density over the volume. Well, in this case, we replace the integral of a 3D charge density over a volume by the integral over the linear charge density over a line. And we'll integrate over the entire source from z equals 0 to z equals L. Well, lambda is a constant, so this works out to be lambda over 4 pi epsilon naught r times, well, and the integral of dz just gives us L. Notice that lambda times L, that's just the total charge. So this is Q, total charge on the rod, divided by 4 pi epsilon naught r. So the hallmark of the monopole term is that our object just looks like a point charge. That is, the monopole term gives us the potential that a point charge that carried the same charge as our object would have if it sat at the origin. The next term is the dipole term. And the dipole potential is 1 over 4 pi epsilon naught r squared times the integral. Again, now we're integrating over a line. So we have lambda times r prime times cosine theta, and we're integrating over z from z equals 0 to z equals L. Okay? Notice that as we integrate over this path, r prime is just equal to c. Okay? So this becomes just lambda over 4 pi epsilon naught r squared, and then we have our other terms. Something else to notice. Cosine theta, the angle between r prime and r, okay, where r is the vector out to the field point, that remains constant as we integrate over our term. So we can take that out as well. Okay? And what we're left with is lambda times, I'm sorry, we had already took lambda out. What we're left with is just r prime, which is z. And so we integrate that from 0 to L. And this gives us lambda times cosine theta, 4 pi epsilon naught r squared. Those were the constant terms. And then the integral gives us L squared over 2. Okay? So we have lambda L squared over 8 pi epsilon naught r squared times cosine theta. Or I suppose we could write it this way. Lambda times L is Q. So this is the charge times the distance, or the length of the object, divided by 8 pi epsilon naught r squared times cosine theta. And so that's the dipole term of the potential. All right? Draw a box around that. We could continue and evaluate the quadrupole terms in the potential and the octupole term and on, but I think we'll stop here. All right? So, very good.